about over-committing Yarn resources. And so why would we decide to overcommit Yarn resources? Well, we had a problem. And that problem was underutilized cluster resources when our cluster was maxed out. So this graph here, up at the top, you can see that there's this black line, and that represents the utilization is being reported by Yarn. In this case, we're using the capacity scheduler. So this is the capacity scheduler utilization. If you go to the scheduler queues, it'll show what the overall utilization of the root queue on that cluster is. And so that black line, you can see that at periods of time, we actually plateau on this research cluster. And when we plateau, down at the bottom, you can see sort of the same thing. This is plotting the actual memory of the cluster, which sort of closely follows that black line. And you can see the red line, that straight line, that's sort of the total size of the cluster. And the red line is basically showing our allocation within that cluster. So you can see that down below, we have these purple and blue lines, which represent memory and CPU utilization correspondingly. And the problem we have is, Yarn will tell us, your cluster is totally full. And we actually look at the nodes, and the nodes are like, I'm not totally full. I actually have quite a bit of room to grow. And so, if you just look at Yarn, you're thinking, well, I have more stuff to do. It's full. I have to throw more nodes at this problem. When in reality, the nodes are telling us, you just need to give us more work to do, right? There's not enough work happening here. We need to do more. So what we're trying to do here, a lot of our jobs are CPU bound in practice. When we look at them, they're basically pegging a core for each task. So we're trying to close this gap, where when Yarn says we're full, we'd like the CPUs to show, yes, I'm closer to being totally out of CPU as well. So the memory shows that we have some room to grow more containers, so we're going to try to load more containers on the node than the node might originally say. That's basically overcommitting, much like how airlines book more seats on a plane than the plane actually has. Similarly, we're going to book more resources on the nodes than the nodes actually have. So, of course, some of you are saying, well, your real problem is not that. Your problem is your jobs are not properly tuned. And that is definitely true for some of our jobs. We have an internal tool, it's called Downsizer, that uses Yarn metrics, uses metrics from application frameworks like MapReduce and things like that, the counters, to automatically figure out, it does analytics on that data, and it figures out, hey, this user is running this pipeline with these jobs. They're asking for way more memory from Yarn than their containers are actually using in practice. So for example, like maybe they're running MapReduce jobs, and their maps are asking for 10 gig containers, and they're using like 1 gig in practice, right? That's a huge waste of resources. And Yarn doesn't know yet. Yarn's just saying, OK, I'm going to allocate this 20 gig for you. And, it doesn't actually directly monitor it to figure out are you actually using it or not. So that tool, we do actually have users that are tuning their jobs. That's improved quite a bit. But that still wasn't enough. And the reason that's not enough is there's also application framework limitations. So let's say you have the most eager user in the world. They're like, I really, really want to do the right thing. I want to be a good citizen on your cluster. I want to try to optimize my job perfectly. So it is being a good job on this cluster, sharing the resources with everybody else. The problem is that the application frameworks often don't have the granularity you need to do that. So for example, let's take MapReduce again. This is true for also Tez or Spark, things like that. You can configure how big your maps are, and you can configure how big your reduces are. But skew is a very common problem in big data, right? So you have a few maps that take far more time and actual resources than the rest of the maps do. With MapReduce, you can set that value once. And of course, it has to be the worst case for your maps, otherwise your job will not run. So you have to set it for that worst case scenario. All the other ones run underutilizing that worst case, except for your few that need it. And then similarly, even if you had a framework that could optimally tune per container the size it actually needs, this graph down here shows that, let's say here's a container. The blue shows the utilization of that container over time. And at the end, we fully utilize that container. That white area, most containers, they'll start out and they'll grow over time and fill their container. That white area there is all underutilized resources, opportunity that we're not using at all. We could use it for something else. So that's sort of the idea. So the other thing that would come up is, why don't you just statically overcommit? And what I mean by that is, why don't you just configure Yarn and the nodes to say, I'm a certain size. Let's just lie and say I'm a few gigabytes bigger than that. Like, ignoring the kernel and buffers and all those things you normally would reserve for. If you're actually not using your resources fully, maybe I can just overcommit statically. Just hard code, this node is actually bigger than it really is. And we've done this. We tried this to some degree. Had some successes with it, but the biggest problem with it is you are going to have cases where somebody actually tunes their job, or in some cases misconfigures their job, runs it with too small of a container size, too small of a heap, goes into full garbage collection on every task. And then your nodes get loaded up with this fully optimized, fully utilized container. And now it really is. It's like the airline case, right? All the passengers show up and they're, where's my ticket? And now we have to hand out $400 vouchers to all of our users because we can't fill their seats. So what's really bad about the static overcommit is the OS starts to kick in, right? It starts swapping. The kernel's like, I'm out of memory. I'm going to start shooting processes. So it starts shooting things. Not necessarily the things we would like it have to shoot. It just decides on its own. And then, on top of that, the resource manager then sees, oh, look, there's resources freed up on this node. I think I'll load it up with some more. So it throws more stuff on that already heavily overloaded node that just shot some things to free things up. And now you're just aggressively making it worse. Because the resource manager doesn't really know, because it thought, well, the node's that size. Look, there's free resources on it now. I'll throw even more on it. So static overcommit, it can work for a while, but when it gets bad, it's very bad. So we'd like to make that a little bit smarter. So we decided to implement sort of a prototype for overcommit, and we sort of had some initial design goals for this. There's efforts in the community to do a similar thing, but we wanted to implement something like just a proof of concept to sort of try some of these ideas, something we can implement and deploy very quickly. So this is something we just did at the beginning of this year, implemented it in about a month or so, and started to deploy it. It's now in production on some of our clusters. The main goal is to try to get this deployed quickly for us. Implied no changes to applications was one of the main goals. If doing overcommit for us meant we had to change the application frameworks, had to change the applications themselves, there's just too many. We have a very heterogeneous load on our clusters. We have lots of MapReduce, Spark, Tez, Pig, Hive. There's custom frameworks, lots of things on our clusters. We have to go to all of our users on these clusters and say, could you please try this for us to see if we can get this to work? It'll just take too long to get everybody on board. So that was one primary goal. We don't want to change our applications to try this. Similarly, we didn't want to make massive changes to the scheduler or to Yarn or the protocols. And for two reasons, right? One is, if we're doing that, that doesn't sound like a quick prototype. That sounds like a major undertaking that's very risky. You're probably going to destabilize something. And also, even more importantly for us, if we do that, that makes it very hard for us to stay close to the community, right? If the community puts in bug fixes to the scheduler, things like that, now they're not applying, those patches don't apply cleanly to our build, and now it's harder to keep up. And it's also harder if we want to propose this to say, hey, everybody, we tried this. If it's some like 700K patch to the scheduler, nobody's going to get very excited about that. So it's a complete rewrite, and we didn't want to completely rewrite it. So we're like, can we implement something that's just kind of on the periphery? We don't want to change the bowels of the scheduler itself, just something on the periphery we can sort of like grow the scheduler and then let the normal scheduler queues divvy up that extra capacity. That's sort of the basic idea. So also, we usually want to overcommit on memory only. Again, when we fill the cluster, we're filling in terms of memory first. So we're going to say, let's try to attack that problem so Yarn can allocate more memory. And then that'll hopefully bring up our CPU utilization with it. Similarly, to roll this out quickly, in theory, all the way to production, we have to be a little bit conservative, right? We don't want to be too aggressive about growing the cluster size, such to the point where we do overcommit to the point where we actually have to shoot containers. The utilization gets so high we have to shoot things. If we're doing that aggressively, then we're going to have users complaining, my jobs are constantly getting shot, I'm not getting my SLAs met, things like that. So we want conservative growth, but we also want rapid correction. We don't want to just sit there like the static overcommit case and constantly throw more data, more work on a thrashing node. So those are sort of the high-level goals. So for those of you, this is the 3 o'clock hour. This is the sleepy time hour. So for those of you who came and like, OK, I'm totally going to sleep in this, this is programmer art, box, and sticks. This is your cue to sleep. So everybody ready? Go. All right, so this is really basic design overview of Yarn. You have the resource manager controlling the scheduling. You have the node managers, their heart beating into the resource manager. And then you have the application masters running on that cluster, the cloud of machines in the cluster. And they're basically getting container assignments from the resource manager, taking those assignments and launching them on the node managers. That's the basic Yarn design. Our concept was really pretty simple. The resource manager is where we wanted to focus as much of the logic as we could. And there's a couple reasons for that. One is we could iterate that design very quickly. So we deploy this to the cluster. If we want to change something, we're just changing the resource manager. We can just iterate, either worst case, restart that node. We don't have to redeploy the whole cluster every time. Okay, so that the basic sort of logic of when to overcommit, how much to overcommit, that's all focused in the resource manager. And the node managers, what they do is they report their node utilization in the heartbeat. This is a feature that was implemented by the community in 2.8. We backported that to our currently 2.7 based release. And so then we use that utilization report in the resource manager to decide when the node should be overcommitted. Sort of interestingly, the node doesn't actually know how much it's being overcommitted or the fact that it isn't even being overcommitted per se, right? What its only purpose, the only thing we added to the node manager at all was this self-preservation logic. The idea being is we were worried that if the node started to become overcommitted and there was too much applied to it, we didn't want to wait for the resource manager to detect that through a subsequent heartbeat and a round trip saying, well, maybe it's a little too high. Hey, node manager, why don't you shoot something to make room? We're worried that if it gets bad, it could get bad very quickly, maybe to the point where the node manager is having a hard time getting into heartbeat because it's slowing itself down. So we have the node manager have a self-preservation mechanism. So it decides when it's just above, it's too high. It's so high, I think the kernel's about to take a decision for us. Then it decides and it shoots containers, preempts containers from an overcommit perspective to bring the utilization back down to an acceptable level. So the resource manager's not killing any containers, only the node manager does. And the resource manager is the only one that actually knows what the overcommit is. It's just changing its internal bookkeeping of how big it thinks the node is. The node itself is sort of blissfully unaware of how much is being overcommitted. It just knows utilization and when to shoot. Okay, so how does the resource manager do that scaling? So we have sort of a high-level watermark and a low watermark represented by the red and orange lines in this top graph. And what we do is when the utilization being reported by the node is below the low watermark, we simply treat that as sort of a full overcommit state. Like the sort of desired target ultimate growth of that node could be the maximum that we want it to be. So as long as the node keeps reporting lower than the low watermark utilization, we'll increment over time the size of that node inside the resource manager so it'll keep allocating more resources on that node. And if the utilization keeps coming back low, we'll keep doing it up to some cap that can be configured. And if it's above the high watermark, then we're actually aggressively scaling back, meaning we don't want to allocate any more containers on that node. At this point, the resource manager is like, whoa, the utilization is pretty high. Putting any more containers is just going to make this worse. At that point, the resource manager is tracking the size of the node very closely at the level it's currently allocated to prevent further allocations on it. And so you can see that sort of in the bottom graph here. This is sort of a view of the node from a resource manager's point of view. The blue being containers that are allocated on the node. That's why it stair steps up and stair steps down as containers are allocated and released, just from a bookkeeping perspective. And you can see that when the utilization is above that red line, the orange line, which is where the resource manager is sort of advertising to itself how big the node is, directly follows that blue line. We don't want to allocate any more space. But it also doesn't decide to shoot itself. It's just saying, well, I won't allocate any more. I'll just let it naturally drain these containers out. Now, when it's between the two lines, then we linearly interpolate the desired size, ultimate desired size of that node for where we want it to go. Now, again, one of the design goals was to be a little bit conservative. One of the things we were worried about is that if the cluster starts up completely empty, the course utilization will be 0, and it'll think all the nodes should be maximally overcommitted. The thing we're worried about is Yarn can be pretty efficient at loading up a node pretty fast if there's enough containers ready to go on that node. What we don't want is to go from no utilization to suddenly I maximally put all the containers on that node without really knowing how those containers behave, and suddenly they all start growing at the same rate. We get really bad. We have to shoot a whole bunch of them after doing a bunch of work. So instead, we have this concept of a float or an increment where we basically say, well, I'm currently at this utilization, or this node size. I want to be a little bit higher. Instead of growing the full node size, I'll go through an increment to sort of grow there over time, growing container by container. And so that's the sort of stair step of the orange curve, again, on the left-hand side here. When we're under the utilization, we'll stair step up to a desired height of the node rather than just jumping straight there and possibly loading it all up at once with dozens of containers or hundreds of containers. So That's the sort of basic concept. The way we control these is parameters. So we have, a bunch of these all have the same prefix listed there at the top. There's a max factor, which is where you're configuring, you're telling the resource manager, this is the maximum overcommit I'm comfortable doing. So this value is basically takes the node size reported when it registers, and it multiplies it by this factor. And so on our cluster right now, it's currently set on this particular cluster to 1.5, meaning it will grow 150% more than the normal node size, or a total of 250% of the original node. So our cluster could, theoretically, grow as high as 2.5 times its original size. The low watermark and high watermark, these are the resource manager's concept of when it sees the reports from the node managers. Those are those target lines, the orange and red lines respectively. So we set those to 60 and 80% of memory utilization. So if it's below 60%, we're going to grow it up to, theoretically, a high of 2.5 times the total size of the node. If it's above 80, we're not going to put anything more on that node until it falls back below 80. And then the increment, or that float I talked about, on this particular cluster is set to 16 gig. On other clusters, it's set a little bit smaller. One question you might have is, well, what happens if I want to run containers that are bigger than that float? Will it never allocate them on the node? And our initial version of the prototype, that's exactly what happened. We overcommitted a little bit, and then suddenly it stopped. And we realized somebody was running something on the cluster that wanted like 90 gig containers, way bigger than the float was. And the node would just not launch it. It would try to reserve it, and then it couldn't allocate it. So we did have one extra thing we added to the algorithm, which is if a reservation appears on the node, which is the scheduler's desire to put something on the node that it doesn't currently have room for, if the utilization shows that the desired target space can fit that container, we'll go ahead and grow that one container. Again, we want to grow, ideally, a few containers at a time, give them a little bit of time to soak. Yes, it looks good, we'll keep going. Speaking of soak time, that's this last property, the increment period. This is a configurable delay between subsequent increments of the node size within the resource manager. So if you want to sort of be conservative and say, I'm going to let one grow, I'm going to let my container bake there for a while to figure out how it's going to behave, and then before I grow another one, you can configure this to be. And originally we had this at 30 seconds. On this particular cluster, we actually ended up lowering it over time all the way down to 0. We put no delay in. That's because this cluster it's particularly high churn. There's lots and lots of jobs with relatively short containers on it. They were coming and going so fast that if we made that 30 seconds, they would leave before the next one would come, and it never would grow above one extra container or so. So in this particular cluster, it's set to 0. Other clusters we have it deployed on, it's set to 10 seconds or so. The important part about these is that, again, it's on the resource manager's view only, and these are all refreshable. We don't have to restart the resource manager. We can change these values, just run an rmadmin refresh command, and it instantly takes effect, and that adjusts the nodes over time. Again, not shooting any containers, just adjusting them over time to try to match the new targets that we configure. And so that's been really useful when we go to play with these on real clusters. So on the node manager side, this is the self-preservation thing I mentioned earlier. Again, the node is watching its utilization, and we set these two watermarks, a high and low watermark. The high watermark triggers a preemption. This is where we don't want to be if we can help it. But if the utilization gets above this level, then we're worried that, again, the kernel is going to start making decisions on our behalf. We'd rather not do that. Let's make a decision ourselves. It will then start preempting things to get down to the low watermark level. So it's sort of like start preempting here. If we get here, preempt down to this level. And both these are configurable. And when we go to preempt, we wanted to try not to just preempt random containers. I mean, it's effectively what the kernel will do in some sense, right? So instead, we wanted to try to minimize the amount of disruption to the cluster. And so we have 4 basic groups that we order them in, and we visit these containers in this group order. So the first thing we're going to look at is tasks that have been run from a preemptible queue. So we have a lot of clusters where they have a preemptible queue. On our clusters, it's the default queue. It's where people can submit ad hoc jobs, things like that. Our users are used to those queues being sort of chewed up by regular production-type jobs or sort of more important jobs. And so if we preempt containers in that queue, that's not terribly surprising to users when things get busy. So that's our first thing, is tasks in that queue. Tasks in preemptible queues. Next would be application masters in those queues. We try to kill tasks before application masters because many of the frameworks, if you kill the application master, it'll end up killing all the containers anyway for that whole app attempt. So we try to kill the tasks first, then the application masters, and then likewise the tasks and application masters in non-preemptible queues, sort of like more production type loads. And again, within each of those groups, we order the containers within those groups for candidates for preemption by their lifespan. So we try to kill the youngest ones first to minimize the total amount of work lost when we have to do this. So that's the node manager's self-preservation logic. And here's the two tunables that are designed for that. You might notice that these are set to much higher values than what the resource manager's been told. And again, so the resource manager is kind of target between 60 and 80%. That's sort of the linear interpolation mark that it's using. This is like 95%. When we get up to 95% utilization, we're like, this node is pretty darn loaded as far as memory goes, and we're worried that the kernel is going to start swapping or killing containers outright. And so 95, 92 are the settings we have on our cluster right now. OK, so these are the results we got. So on this cluster with those settings, this is that same cluster about 2 months later after we rolled it out. And again, same graph type. The black line is utilization of the cluster as reported in the scheduler page. The bottom graph is a little bit different to look at now. Now we have an additional black line showing the actual true size of the cluster as far as the hardware is concerned. What we originally was telling Yarn, this is how big the nodes are. That dark red line is showing the size of the cluster that the resource manager believes it is with the overcommit turned on. And the thin red line below it is the actual allocated resources within the total. And so you can see that this cluster basically overcommits almost all the time now. And you can see at the top that the CPU utilization is significantly higher. I mean, before, the utilization was hovering like around 40, 50%. Now it's hovering, especially during the PEG things, it's hovering closer to 70, 80%. So that's a significant improvement for us. It's like close to 40, 50% CPU utilization improvement. And so that's been a big deal for us, right? This is like down at the bottom again. You can see that in terms of the Yarn size of the cluster reported, it's like 50% bigger, which is like taking your cluster and putting half again as many nodes on the cluster without actually buying those nodes. So that's a really big deal for us. So another thing you might ask is, say, OK, that's great, but how many times did you actually shoot things? Because I suspect you actually had to shoot things. And the answer is yes, things were shot during this experiment. So we did expect this, actually. This is something we anticipated. We were worried about it. But what surprised us was how little was shot. We expected shooting to be a regular thing, and it turns out it wasn't. So this graph is trying to show this sort of the relative scale of those things. The dark blue line is showing, for that same period I just showed you with the previous results, it's showing, the dark blue line is the amount of capacity that we're gaining due to overcommit in terms of gigabyte hours. And the light blue line at the bottom is showing how much we shot. And you can see it's basically zero. The actual numbers here, if you sort of integrate the curve and figure out total amount over the whole week, it was like, I think we gained 3.3 million gigabyte hours of extra capacity on this cluster. And we ended up shooting a total of about 509 gigabyte hours of work. And I think on average, the containers that were shot lived on the order of like single-digit minutes, worst case. Yeah, I mean, it was just, there wasn't a whole lot of work shot. Other anecdotal evidence for this is, again, when we rolled this out, to date, it's been on our clusters for a few months now. And there's not been a single user who's come to our group and said, what did you guys do to the cluster? My job's slowing down. I'm seeing containers getting killed, preempted, things like that. Not a single user has mentioned this. We have had groups come to us and say, what did you guys do? Because I used to allocate big containers, and I would wait minutes for it. Now they're allocated much, much faster than that. Did you guys do something? So we've only ever heard a user say this has just been better. We haven't had anybody complain whatsoever since we've turned it on. So what are like some of the major lessons learned? Of course, the main thing is as the results showed, we had significant overcommit was achievable with real workloads on our real cluster. I mean, this is our main research cluster. All of our main research jobs run on this cluster. It's not like this is some arbitrary load that we made up to try to get these numbers. We didn't tell users to do anything about this. We took a real cluster. We did this to this cluster without, with the load it already had. The other thing that sort of surprised us is even though we were conservative going in, we expected there to be a lot more cases where we would get caught, where we think we can put these containers on the node, and it turns out, no, they all grew in unison, and we made a mistake, and we had to shoot something that had been running for tens of minutes or something like that. And this does happen. occasionally, but it's really, really rare for us in practice. It's so rare that users basically don't notice. They treat it almost like it's a regular task failure or something like that. We also noticed that, again, container reservations, really more than the float, the container reservations drive that overcommit. That little bit of advertise entices the resource manager to say, OK, there's a little bit of space in here. I'm going to reserve it. And as soon as it reserves it, we allocate the one container. And the reservations drive the growth up for the overcommit. Coordinated reducers can still be a problem. And what I mean by that is just for the general concept of tasks on a node acting in concert. So coordinated reducers is an example of this. What I mean is, like say you have a map reduce job, and it has skew in the map phase. There's one map that's trailing. It's waiting to finish. All the reducers have spun up, and they're waiting for that last map. And if a lot of those reducers are scheduled on this one node, for example, they may all sit there, underutilizing that container. They're just in the shuffle phase, waiting for that last map to complete. That last map finally completes, and then in concert, they all sort of coordinatedly go get the last map data, and then start the intensive reduce phase, and then all grow over time. And so then you have a case of like, well, initially when they were in that last shuffle phase, they were pretty quiescent and looking pretty good. And then suddenly they all in concert grew together, and we can run out of memory. We can overcommit in that case to the point where we have to shoot something. That can happen. We have seen it happen. It just in this particular cluster with this heterogeneous load, in practice, that coordinated lineup on a node doesn't seem to happen too often in practice. So that was surprising to us. We thought we would get a little more shooting than that. And again, cluster totals over time, that is the one thing that was sort of confusing. We have a group that does a lot of our internal metrics collection and sort of graphing sort of tools team for cluster totals. And they were like, what's happening to the cluster size? Why is the cluster size moving all over the place when it used to just be a straight line all the time? And so that can be a bit confusing when it starts to grow, especially since this is a very simple prototype. It just commits on a node-by-node basis. So for example, you will see the cluster overcommit before the cluster is anywhere near being full, because it just looks at an individual node and say, one node might have a whole bunch of containers loaded on it because let's say it has a lot of locality for a particular kind of job, and it puts a bunch of containers on that node. The node right next to it might have hardly anything on it, and it'll decide to start growing that original node that looks pretty full but yet has some extra space based on utilization, and that yet you still have many terabytes of free in the cluster, which is a little bit, most people would expect you wouldn't start overcommitting until you really kind of have to. There's nowhere else to put containers. This simplistic prototype, just doing node by node, will overcommit before the whole cluster is kind of totally full in a sense. So that's also a little confusing. All right, so again, this is just a simple prototype. It's on Yarn 5202. That's the JIRA for it. More than happy to have people try it out, have comments on it, answer questions on it, things like that. If you want to try out the prototype or take a look at the code, that's where it is. Again, like I said, it only grows the cluster as a whole. It doesn't grow individual queues. So we've had cases in the past where our clusters have many queues in them. And let's say that one queue gets really busy, but it's a relatively small queue. The rest of the queues are not that busy. What can happen is that queue might not be big enough to drive the whole cluster strongly enough to move all the nodes to want to overcommit. And so one idea is, well, is there the concept, maybe could we overcommit per queue? Like maybe we grow nodes and give the extra capacity just to particular queues instead of all the cluster. That would sort of involve a more invasive change to the scheduler itself, which is why initially for this prototype we didn't address that. But that's an area we could potentially look at next. Other things, like I mentioned before, nodes can overcommit before with others being relatively idle. That can be a bit confusing. CPU overcommit, we recently rolled this out to our research cluster. Just literally last week. Initial results are really good. What happened was we were overcommitting on memory. Now, when we started growing that cluster, it started hitting CPU as the resource it started running out of for purposes of allocating. So CPU overcommit lets us grow that as well. And so now we're pushing that cluster even higher than it was before. Another potential idea is predicting growth based on past behavior. What I mean here is that if you're running a regular pipeline of data, your jobs can be pretty predictable in a way. Some of them can. And so one of the things we could in theory do is have Yarn be a little bit more proactive rather than reactive. Right now, it's purely reactive. It just watches what happens in the cluster and says, oh, wow, OK, I made a mistake. I'm going to have to shoot something or scale back on what I'm doing. If it knows saying, hey, I always run this job always has these containers that are always 12 gig, and I say I always know that 30 minutes into these containers, they go haywire. If it knew that, it could try to avoid situations where I spend a lot of time, had to shoot containers that have been on the cluster for a while. And finally, and most importantly, we really like to integrate some of the findings and ideas here with what makes sense into Yarn 10.11. So Yarn 10.11, what is that? That's sort of the umbrella jar for the community for doing overcommit. We believe that that is, long-term, the best solution for doing overcommit. And the reason I say that is because it has the concept of guaranteed versus opportunistic containers. And we find that that's really important for trying to deploy to a lot of clusters where people are like, you know what, I'm really not comfortable with you being able to shoot literally anything on my cluster, right? Because I might have a very latency-sensitive job or an SLA production job that I'm like, I want some guarantees that Yarn's going to do everything it can not to shoot this, right? I don't want to go out of my way to shoot it. And the prototype we have will not guarantee that, right? Anything, in theory, is eligible. In worst case, we can shoot application masters in non-preemptible queues. Despite it being the last group, it could happen. So, so Yarn 10.11, I think, is the best long-term solution. The reason we didn't go with it is, again, we wanted something, we were getting pressure internally to try something to leverage more of our nodes faster. And that design is significantly more complex, and we were worried that by the time that was sort of robust enough to deploy in production, it was a much past our time frame. We want some initial results to help feed back into that design. But again, as I listed here, it promotes containers from opportunistic to guaranteed. Has it's a pretty sophisticated design, and I think long term that's going to be the best solution. Okay, finally, I'd like to acknowledge some people with this. Nathan Roberts, one of my coworkers at Yahoo, was very instrumental in helping to develop this prototype. I also like to give a shout out to a couple people in the community that made some instrumental changes that we directly used as part of this. Inigo and Giovanni both did works on some of the protocols between the node manager and the resource manager to help drive utilization between the node manager and resource manager, which of course is sort of a fundamental piece of this prototype. And then finally, I'd like to also shout out to all the people that have been working on Yarn 10.11, contributors, commenters, because again, that's the vision we see as the ultimate long-term solution for having Apache Hadoop do overcommit. So with that, any questions? Thank you. Yes.
So I have a few questions. The first one is, so in our environments, we have seen that there are containers whose memory sort of consumption changes over its life cycles. So when the container is just launched, its memory consumption could be pretty low. But then when it starts fully up, the memory consumption also grows. So in your current implementation, is there any mechanism to cope with this kind of changing memory requirements during the container's life cycle?
Okay, so to repeat the question real quick, so sort of paraphrase it, make sure I have it right. Basically, it sounds like they have a case where there are containers that they start up and they're underutilizing the resources for quite a while, and then at some point they'll rapidly grow their utilization and fully fill their container. And how does this initial prototype deal with that? It doesn't directly, and this gets back to the predictable part, right? It's purely reactive, so it doesn't know that containers will do that. Even if you have containers that do that, there still is a lot of opportunity to leverage it. So for example, that original graph I showed, showing the container being fully utilized at the end, but there's an initial part where it's very low. Depending on how long that is and how short other containers might run within other jobs, you can definitely fill that space, and our prototype does fill that space. So for example, we have things like that. We have Spark shells that are very popular with some of our researchers. So they'll spin up a Spark shell. It's almost like a cluster within a cluster. And they'll load up and cache some data, and then they'll wait, and then of course it waits there until you type in some sort of interactive query to it. When you do, then it gets very busy, but in between queries, it's relatively quiescent. And so we've had cases like that, and it still works pretty well because while it's quiescent, that amount of period of time is not necessarily predictable, but we have a lot of, especially with MapReduce, some short-lived containers, relatively short-lived containers that can fit within that extra space, get their work done, and get out. And so in that sense, we do benefit from that, even in that case. So
one more question.
Yeah.
Do you have to do anything special to cope with the OM killer on the memory?
So with the out-of-memory killer, in practice, we've never seen the out-of-memory killer kick in. Again, part of that's because we don't actually see too many preemptions in practice. We see probably a few hundred preemptions a week on this cluster. I mean, in terms of scale, this is a cluster that's running hundreds of thousands of applications a day. it's running millions of containers over that week. So killing a few hundred over that week is basically almost nothing, 0.01%, I think, relative to how much we're gaining from overcommit. So no, we've never really, this doesn't have an explicit tuner to the automatic memory killer. I think Yarn 10.11, there's been some of the sub-areas people have talked about having Yarn explicitly give hints to the automatic memory killer, saying, well, if you really do end up kicking in, let me give you hints about what not to kill. Please don't kill the node manager. Please don't kill the data node. Things like that help the out-of-memory killer if it does. But again, I think the intention from the open source community is to not have the out-of-memory killer make the decision if possible. So, other questions? Yes.
I had a comment and a question. So comment is about the recurring jobs, right? So you mentioned this is quite interesting, and what we did in the work with Rayon for reservation system is for handling recurring jobs, where we actually reserve resources ahead of time. So you have the plan of what the job is going to run.
Oh, yes. So yeah, this actually, yes, you're exactly right. So the question is, with reservation system, the reservation support that Microsoft did in Yarn, I don't know if you guys are familiar with it, it's the ability for applications to sort of tell Yarn ahead of time, I have a critical job that's showing up tonight at 7 p.m. It's going to run for 2 hours, and it's going to take up this kind of resource pattern. This is something that we could feed that knowledge back into the overcommit thing, right? It could predict and say, OK, I'm going to need to carve out some space. I know I'm going to have containers that I'm going to have to move out of the way if they're still around at 7 p.m. to make room for this reservation. So. Yes.
But you also mentioned that you look at 4 orderings for preemption, like the preemptive, not preemptive.
Correct.
But that information is not available to the node actually, right?
Yes. So as part of our prototype, if you look at our prototype, we did add the knowledge. So the AM knowledge was already there. That's the part that Giovanni added that I mentioned before. That's there. We added another bit, which is basically, is that container part of a non-preemptible queue or not, as part of the container token. So that is something we did add. Again, we tried to avoid changing all Yarn protocols. That's the one thing I think we did change. Again, it's not ideal. The node manager doesn't necessarily have the perfect information to make the best decision about that. But for purposes of our prototype, we really wanted to focus on try to shoot tasks that are in queues that already are being shot today on some of our clusters. In other words, users are kind of somewhat used to that. And the second thing is we really wanted to prioritize minimizing the loss of work. So there are cases you could have, for example, let's say you have a user who's heavily using the cluster and another user who's just started to use the cluster. They have a very small percentage of it. They're not getting nearly the same fair share that some other user is. The node manager doesn't know that, right? So when the node manager goes to kill something, it might do something what is deemed not very fair. It might shoot containers for that one user who's getting severely underserved and avoid shooting the containers of the person who's dominating it right now. That is, again, that's part where that prototype doesn't address that per se. For purposes of our prototype, we wanted to, again, make the node manager be highly reactive. We were worried about that round trip time, that by the time it decided to take action, in some sense, what we tried to do instead was, and this was borne out by the fact we don't have very many things shot, is to have the resource manager not push it near where the node manager's like, I'm going to need to take action. It's more literally the node manager's like almost like a last resort thing. So we try to have the resource manager not make that bad decision in the first place if it can help it. Yes? Yes, exactly.
But then it all depends on the application. For example, you may have an application where it's not good at distributing the load.
Sure.
There could be a bug or whatever. It's not good at that. You have 200 node cluster, but then your application only line up on a few clusters.
Correct, yes.
And then this whole overcommit is limited. Is that correct?
It is, yes. So this prototype, just to be perfectly clear, this prototype is relatively simplistic in the sense that it just looks at individual node-by-node basis. It's not looking across the cluster, which is why you can have cases I mentioned before where the cluster will start growing itself for its total size before the cluster utilization is anywhere near 100%, right? So, and you could look at that 2 ways, right? You could look at it as, well, I'm taking this node that's heavily loaded, and I'm making it grow because, I've already loaded up the containers to its original size, and I'm even growing it more when a node right next to it might be completely empty, right? This will do that. Now, in one sense, you're saying, well, that's silly. I'm risking killing containers in this node when I could put it in a guaranteed slot in this other node. And on the flip side, well, what is it about that node that's so popular? If that node really is amazing to all these applications, shouldn't we maybe let more applications want that node. I mean, they really want that node badly, right? I mean, for some reason, they're on that node. So, I mean, you could see it both ways, right? It might be a bad thing to do, but in some ways, it might be a good thing to do. It depends on how important that node is to those applications and why it's lopsided in the first place.
My question is that leads me to the next question.
Sure.
Instead of focusing on overcommitting, can we have yarn that try to run jobs on the cluster that is not used, nodes that is not used?
Yes, yes, and so this will happen. Part of this it'll do a little bit of a hybrid of those two things. So the question is, can we have yarn be a little bit smarter and not just continue loading up a node that's already overloaded, use some of the empty ones? And part of our conservative growth approach does buy you some of that. So it will start growing that node, but again, since we don't grow it instantly, we grow it over time. It takes time for that node to grow. And during that time, Yarn will sit there and keep seeing these other nodes heart beating in that have space, and will eventually say, you know what, maybe locality isn't the best thing ever. This is a node in hand. It looks like the one with locality is kind of busy right now. I'll go ahead and put some containers on there. And that will happen. So because we grow it slowly, and you can configure how slow it grows. If you configure to grow it particularly slowly, Yarn will decide, you know what, I'm not going to wait for this node anymore. I'm going to take these other nodes that have space free, and we'll spread that load. Yes?
I'm sorry, if we could take the rest.
Oh, I guess I'll take the rest offline. I'll be outside after the thing. So thank you guys very much.
Sorry.
No, that's totally okay. Totally okay. Thank you.